Hello everyone, I am Jin Yeying from the National University of Singapore. I'm going to talk about our ECCV22 paper, Unsupervised Night Image Enhancement, when layer decomposition meets light effects suppression. First, I will give an introduction to the night problem and motivation and challenge of this work. Night image has two problems. One is the low light problem, another one is the light effects problem. Existing low-light enhancement methods can enhance low-light regions. However, they will over-enhance light effects regions. Existing night dehazing methods cannot enhance low-light regions. Although they can suppress glow, they cannot suppress light effects in the clear night. The main task of this paper is to boost dark regions, at the same time suppress light effects. The main challenge of this research is the lack of paired training data. It is hard to collect the ground truth of these images. Rendering physically correct night light effects images is also challenging. Therefore, we propose an unsupervised night image enhancement method. The key ideas are model-based layer decomposition, together with the unpaired light effects suppression. Next, I will talk about key ideas and contributions. The first idea is layer decomposition. Layer decomposition means given input mixtures, how we can decompose or recover the individual original layers. The second idea is unpaired light effects suppression. Although paired training data is hard to collect, unpaired light effects free data can be obtained. Then, I will introduce the framework and losses. Let's look at our framework. The input night image goes into the decomposition module. Our decomposition goal is to obtain a background scene that is free from light effects. That is to say, we want to estimate the initial background scene GINIT. Then, we input GINIT into our light effects suppression network to obtain our final output DREFINE. Let's talk about our layer decomposition module. Our decomposition network is based on an image layer model shown in the equation. We output three separate layers. B is the light effects layer, C is the shading layer, and D is the reflectance layer. The gradients of the light effects layer have a short tail distribution, shown in C. Using gradient exclusion loss, color constancy loss, and other losses, we can separate light effects from background layers. Next, let's look into the unsupervised light effects suppression network. We concatenate GINIT with the light effects layer G, then input them into our suppression network. Although paired training data is hard to collect, unpaired light effects free data can be obtained. Using a class activation map, the feature maps generate an attention map. The attention map shows the network is focusing on the light effects regions. Then we introduce our unsupervised losses. Here we use the fused grayscale image. The motivation for having the grayscale image is that nighttime images contain multicolored artificial light sources, different from nighttime color images. Nighttime grayscale images are less complicated. We first use our adaptive fusion to obtain a fused grayscale image. Then, from the grayscale image, we compute features from the fine-tuned VGG. These features are less affected by light effects. We also compute high-frequency features from the guided filter. We next use these features to constrain our network to output DREFINE. Finally, here is our structure and HF features losses. In the end, we come to results and conclusions. We show results on light effects suppression. Here we show results on a public dataset, the dark Zurich dataset. Our method not only suppresses light effects, but also enhances low light regions. Our method is more realistic, light effects suppressed, and has good visibility. In conclusion, we presented an unsupervised learning framework. It can boost dark regions and suppress light effects simultaneously. And our unsupervised losses can restore the background details. Thank you for your listening. Our code and data are publicly available.